So we are ready to go. Thank you, Fabio, for coming. Sorry again for the delay. It took longer than expected, especially the session in the morning stretched a little bit longer. And so Fabio Aiolli is here. He received a PhD, is the next speaker. He received a PhD in computer science in 2004 from the University of Pisa in Italy. He was postdoc at the computer science department at the University of Pisa and a visiting scholar at the University of Illinois, Urbana-Champaign in Illinois, USA, and a postdoc at the Department of Pure and Applied Mathematics at the University of Padova. Since 2006, he's assistant professor at the Department of Mathematics at the University of Padova. His research activity is in the area of machine learning and pattern recognition. In particular, he has expertise in kernel methods for structured data, kernel and representation learning, hierarchical representation, and deep learning, with application to recommender systems, neuroscience, and biology. So what he's going to talk about today is going to give a talk on representation and kernel learning. So as you've seen from the abstract, the success of classification of machine learning algorithm heavily depends on data representation. And also, even the most performing classification algorithm will fail when provided with a bad input representation of data. So in the talk, the problem of data representation for machine learning will be introduced. In particular, Fabio will focus on kernel machines, shuffle-vector machine for classification and regression. And the theory behind this kind of algorithm will be somehow explained, and he will tell us how to build, I believe, also kernel that are pretty effective in classifying the data that we have. So thank you so much. So I guess I recommend that we have 1 hour 15, 1 hour and a half, you see the first part, and then we take a break, and then we'll go for the second.
Okay.
Thank you so much.
Thank you very much, Michele. Now, I think we can start. Yes, I organized this talk basically in 4 parts. In the first part, I introduced from the very beginning, the problem of supervised learning for classification and regression. Then, in the second part, I want to focus more on the kernel representation. And finally, in the third part, in the second part, I focus more on the very simple linear models, which are at the base of kernel methods. And then we see in the third part how the weak linear model can become powerful when introducing kernels. Finally, in the fourth part, we see how the representation can be organized in a hierarchy in a way similar to the deep learning. Okay, so let's start by introducing one of the formalization for a supervised learning problem. So basically, in a supervised learning problem, we have available input, like, for example, in this case, X, which can be, for example, the representation of an email. And we want to obtain a given output, Y, which can, for example, can be spam or no spam with respect to the email. So basically, in classification problems, we have the problem to classify something in one or more categories, while in regression problems, we want to associate to a number, a real number, typically a real number, to an object X. So the basic assumption we make in supervised learning is that we have an oracle, let's say the nature, which basically works like the following. In one possible view, you can imagine to have a probability distribution, and 2 probability distribution, a prior distribution on X, and a posterior distribution of Y given X. And this is also called the stochastic version of the oracle. In the other view, you can see the function f as a simple deterministic function with domain the set x and codomain the set y. So basically, in this case, we have the ideal situation where the probability, the posterior probability py given x is equal 1 if and only if y is f of x. So the basic assumption of supervised learning is that in any of these two cases, both the probability or their target functions are unknown to the learning machine. So basically, what we have is only one typically small set of examples where data have been drawn using the probability we gave before. And we want to select an hypothesis, let's say one function g, from a set H, which is called the hypothesis space. And so basically, based on this training set, we want to get this plausible hypothesis G from the hypothesis set H using training data. And this hypothesis G should be the one that generalizes well on the new unseen data. So basically, if I draw a new example based on pxy, the function g should be able to predict y given x in the correct way. In supervised learning, we basically have two different measures. The error we have on the training data is also called the empirical error or empirical risk, while the expected error of given unseen pair xy is called idle error or idle risk. So basically, this is not possible. This quantity is not possible to be computed, while this quantity is promptly computed by using training data. So basically, in a schematic way, this is our situation. We have the unknown target function there. Then we have a bunch of examples, and we have available an hypothesis set H, and we want to construct a learning algorithm that, based on these training examples and the hypothesis set, is able to pick one of these hypotheses that performs well on new unseen data. So a crucial problem in learning is, so then every possible function is learnable or not? The answer is clearly not. Not every formula can be learnable. So we have to make additional assumptions on which are the target functions we want to learn. So basically, the hypothesis space cannot contain all possible functions. And all the assumptions we make on the type of functions that we allow to approximate, all these assumptions are called the inductive bias. And the inductive bias basically is in two places. First of all, the choice of the hypothesis set. Which hypothesis I want to put into the hypothesis set. Okay? And secondly, the learning algorithm I use, or how I explored the hypothesis set H. These are the two most important ways to put the inductive bias in the play. Okay? So we said that not all the functions, we cannot use hypothesis spaces that contains all the possible functions. So we need a kind of measure to measure the complexity of the hypothesis space. And to compute this kind of measure, we use the concept which is called the shuttering. Basically, the shuttering is of a hypothesis space. We say that a given set of points is shuttered by an hypothesis space when H, the hypothesis space H, is able to implement all possible dichotomies in S, in the set of points. It means that, however, if you take a number of points in S, you can assign any labels to each of these points, and you always find an hypothesis in H that can implement correctly that dichotomy. Another popular, the popular measure of complexity is then the VC dimension. What is the VC dimension? The VC dimension is formally computed as the maximum number of points that can be shattered by H, by an hypothesis space H. If these, if arbitrarily large finite sets of X can be shattered by H, then we say that VC dimension of H is simply infinite. Okay? So let's take an example. Let's take the example of hyperplanes. So basically, hyperplanes in R2 to the 2. Okay? So basically, we have this kind of hypothesis. This is the space where our hypothesis moved, and this is the kind of hypothesis. For example, this hyperplane is an hypothesis of this hypothesis space. Then the question is, what is the VC dimension of this particular hypothesis space? The space of hyperplanes in R to the 2. So to answer this question, we need to show, for example, is the VC dimension greater than 1? The VC dimension will be greater than 1 if it exists one point that can be shattered by in H. And this is trivially true. Okay? So, one more difficult example, let's take 2 points. In this case, we take 2 points. You see, they are always the same points, but any assignment you can choose, you can pick one hypothesis from H that correctly realize this kind of dichotomy. For example, in this case, you have plus and minus label, plus and plus, so you can put the hyperplane like that. Okay? In this case, you have minus and plus, and you take this as the hyperplane. Okay? That correctly separates positive from negative data. Okay? So this demonstrates that the VC dimension of H is at least 2. Because recall that the VC dimension is the maximum number of points that can be shattered by H. Okay? So let's see if this VC dimension is at least 3. So you can see that if you choose these 3 points and you assign any possible labeling to these points, you always find one hyperplane that correctly separates the data. Okay? So this means that the VC dimension of the space H1, in this case, is at least 3. Okay. So the question is now, can the VC dimension of H be 4? In other words, can we choose 4 points that can be shattered by hyperplanes in R2? The answer is not. Okay? For example, if you take these 4 points, but this is just an example, if you take these points, you see that this kind of labeling, for example, negative, negative, positive, positive, there is not any hyperplane that can separate these, they can realize this labeling. Okay? So, intuitively, the answer is that the VC dimension of H is exactly 3. This is not it's not by chance, because you can show that when you use hyperplanes in R to the n, you always have a VC dimension equal to n plus 1. And note that n plus 1 is exactly the number of parameters, free parameters, that we have here in your model. Because you have n parameters to characterize W, and you have plus 1 parameters for B. So the VC dimension in this particular case is equal to the number of parameters of the model. Okay? So now let's study how can we characterize the generalization error. It means how your models, the models that you generate using a given learning algorithm, behave with unknown examples. So we consider a binary classification where we have a training set S, like before, and hypothesis space composed by these Hx, which are parameterized by theta. Okay? And also you have a learning algorithm, let's say L, which return the hypothesis G, which is corresponding to a given parameter, theta, that minimize the empirical error on S. So basically, in this case, your learning algorithm choose the hypothesis that minimize the error in the training data. So the empirical error, okay? Then, in this situation, it's possible to derive an upper bound of the idle error, which is valid with improbability. It means that it's valid with probability 1 minus delta, with delta being arbitrarily small. And this bound is in this form. So basically, this is the idle error, the error that the hypothesis G will have on new unseen data, which is less or equal to the empirical error, which is this one, which is the error that G has on training data, plus this function, which depends on 3 parameters, on 3 arguments. Here, you can recognize the VC dimension of H. Here, you have the number of examples in the training set. And here, you have the delta. It means the delta you used to define how you want this bound to be probable. Okay? So basically, you can recognize 2 different terms. The first term is the empirical error, and the second term, which is also called VC confidence. In the first term basically depends, you can note that the first term basically depends only on the learning algorithm. Okay? While the second term does not depend on this algorithm, but it depends on the training side and increase when the n, it decrease when the n get larger, but also depend on the VC dimension of the hypothesis space. And you see when the VC dimension, which I recall you, it's a measure of the complexity of the hypothesis space. When the VC dimension gets larger, then this bound, this value get larger, and then this bound is not so good. Okay? And finally, it depends inversely on the confidence delta. So basically, the take-home message of this analysis is that when the complexity of the hypothesis space increases, then you need more examples to generalize well. Okay? So this is the point. When your hypothesis space is too complex, you need more evidence to build one good, to get one good hypothesis. Okay? So based on this bound, some years ago, Vapnik proposes this principle, which is called structural risk minimization principle. Basically, it proposed to create a hierarchy of hypothesis space, which increasing VC dimension, and then to select the hypothesis, the hypothesis space inside, which minimized the bound that we have seen before. And this, so basically, what you can observe is that when the VC dimension increases, then you observe less empirical error, clearly, but you have the VC confidence that increases. So basically, sorry, the VC confidence is this. So basically, the bound goes like this. Okay? So the structural risk minimization principle take this hypothesis which minimizes the bound. Okay? So now we finished with this first part. We can just introduce the linear models. I think many of you know the linear model, but basically a linear model is a linear combination of the input, like this, plus one bias term. And note that this formula can also be written like this by setting the one of the coordinate to 1 and including b in the vector w. Okay? So basically, the simplest form you can see the linear model is like this. Okay? How you can use the linear model to make classification or regression? For classification, you can just take the sign of the scoring function f. Okay? So you compute the linear scoring function w dot x, where w is your parameters vector, and then you get the sign. Okay? So you have one of two values, -1 and +1, to make classification. For regression, you can take just the scoring value. Okay? So one of the simplest algorithm for linear classification is the Perceptron algorithm. Basically, the Perceptron algorithm results in hypotheses like this, which are basically linear classification models. Okay? So how Perceptron works? It's very, very simple. Basically, you have a training set like this. So basically a set of pairs. You initialize the weight vector to the null vector. And now, in each iteration, basically you pick a misclassified point xi. What misclassified means? It means that the classification applied to xi is different from the label of xi, which is yi. Okay? So basically, you take one of these points, and for the one of these points, you do like this. So basically, you update the weight vector like this. So you add the x when the label of x is +1, or you subtract the xi when the label of xi is -1. And you repeat from step 3 and 4 until all points are correctly classified. So the question is, but does this algorithm converge? And the answer is yes, but only if the data are separable. So only if there exists one hypothesis, one hyperplane, that correctly separates data, negative points from positive points. So this is the initial situation, for example, and this after some iteration of the perceptron when you get convergence. In this case, all the points are correctly classified. So the algorithm converges. Okay? For what concerns regression, we have a similar. You have a similar algorithm. You can try to solve the regression problem by minimizing the residual error, minimizing the mean squared error, like this. So basically, you can see everything in this form, in this algebraic form, when you put all the x of the training set on the row of this matrix, and you put all the output label on as the value of this vector y. So basically, from this equation, you can try to minimize this error in the training set, maybe regularizing with a squared norm of W. And after very simple derivation, you obtain something like this. You obtain that the weight vector W at the end of the algorithm will be a simple linear combination of input examples, where the combining weights are computed like this. I call this matrix X transposed as K. We see that this matrix basically is a kernel matrix, and we talk about this after. Okay? So now let's talk about representation. So the more natural representation, for example, in this case.
Can you say something about the regularization term lambda, so just in case they don't?
Okay. So basically, this problem, when you don't have this term, this problem can be ill-conditioned. Okay? So basically what we do is to add a regularization term like this with a parameter lambda. So basically when lambda is bigger, you want more regularized hypothesis with where the norm is constrained to be very small. Okay? When you relax on lambda, so for small values of lambda, then you are trying basically to minimize as much as possible the residual error. So this is a kind of trade-off between to keep the norm of the weights small, and on the other side, to keep the residual error as small as possible. Okay? So the more natural representation for images, for example, is just taking the gray values of the image. For example, in the case of 16 by 16 gray level images, you can take just the gray level, okay? But this is just one way. In fact, you can also extract more meaningful features. For example, to get the intensity, to get the symmetry of the handwritten digit, and so on. And so you can, basically, you can obtain something like this that can be a better representation with respect to the original one. So the message I want to, the thing I want to say now is that different representations can lead to very different difficult of the problem. I mean, you can have hard time to solve a problem when you use one representation, and the same problem can be very easy when you use another different representation. Okay? So the representation is very, very important in machine learning in general. Just to make another example, in this case, you have one type of representation, but if you make a nonlinear transformation to the data, like this, for example, you take the vector x1, x2, and you map this vector to x1 to the squared, x2 squared, then you have something like this, which becomes linearly separable. While in the first version, it was not linearly separable. So Also in this case, if you make a nonlinear mapping of your data, you likely obtain something that is better or one problem that is easier to solve with respect to the original one. Okay? Now, consider this linearly separable problem. One question we can do is, here you can see we have different hyperplane that can separate your data. But which one is the best? Do you have any clue about this? Which one of these can be the best one to use as our linear separator? So the answer is clearly the third one. The third one seems to be the most, the best, okay? And why this is the best hyperplane you can choose? This is one question, and we answer to this question in the following. And the second one is, to which double B this corresponds. So basically, after some derivation, you obtain that this W can be computed like this. I don't want to go into the details, but you basically obtain that the margin can be obtained like this. When you put W, basically you obtain the margin like this, and then you want to find the W which maximize this quantity. Basically, this quantity is the length, the distance between this margin hyperplane and this margin hyperplane. This distance is rho, is also called the margin. So the trick here, we want to find the W that maximize this margin. And the one that maximizes this margin is obviously the one that minimizes the norm of W. Okay? And this is exactly the problem of SVM. SVM basically works like that. It tries to minimize the norm of W given the classification constraints. Okay? To answer to the first question before, I propose another question. Can we apply the structural risk minimization principle to the hyperplanes? Yes, because when data are separable, we can say that it exists another bound on the solution of an SVM, which says that the VC dimension, in fact, is not m plus 1, where m is the number of dimensions, but it depends on this ratio. Where R is the diameter of the points in the training set, and rho is the margin of the training set. So basically, this bound depends on this ratio and not on the value of m, which is the number of dimensions. This is a very important result because it explains why maximizing the margin implicitly reduces the VC dimension and then give better guarantees with respect to the generalization error based on the bounds that we give before. Okay? And why we don't care about the R in this case? Because we fixed the representation, so the diameter of the minimum enclosing ball, the ball that enclosed all your training data, is constant in this case. Okay? So the only variable here to optimize is the margin. And this is why SVM tried to maximize this quantity, or to minimize the norm of the weight vector. So, and now we can answer the question before. If you have that situation, basically in all these cases, you have empirical error equals to 1. Okay? So basically you can form an hypothesis hierarchy based on the margin, or equivalently based on the norm of the W, and you obtain this kind of hierarchy. Then, in all these hypothesis space have empirical error equal to 0. So which is the one, then, that minimizes the bound on generalization error, on the ideal error? The one that minimizes the VC dimension, the VC confidence. And the one that minimizes the VC confidence is exactly the one that minimizes the VC dimension, which is the one that maximizes the margin. This is because we need to get the hyperplane that maximizes the margin to have guarantees on the generalization error of your hyperplane. Okay? So basically, the last bound of this session, what time is it?
I had a question. So go back to the previous slide.
Okay.
So you're saying that you build a hierarchy there?
Of hypothesis space,
yeah.
where...
So number 1 is the best one.
Sorry?
According to what you said, number 1 is going to be the one that we prefer.
Exactly, because in this hypothesis space, each hypothesis space contains the previous one. Okay, but if you take the one with C1, this will be the one with minimal norm of W. Okay, minimal norm of W, then maximal margin. And this will be the one that has empirical error equal to 0, but VC dimension minimal. So VC confidence minimal. Okay? So basically, this is the one that you choose. Another bound that is very, very important, especially for what we are saying the following, is this one. So basically, you have here, you have the margin that you can compute when you obtain the W. You can just compute the margin like this, okay? And after that, you can compute the diameter using this formula. Basically, it turns out that to compute this quantity, you need of a constrained quadratic problem. It's not so difficult to compute this problem. Okay, and this, with this, you can compute the radius or the diameter of the minimum enclosing ball, MEB. Okay? Now, let P error, which is the probability to have one error on new unseen data, then you have this bound that essentially says that if you take the ratio on your data, the expected value of the ratio on training set of size n is an upper bound to the probability, to the ideal risk, of the algorithm, the model that you obtain using n-1 example. So one training set of size n-1. Okay? So basically the meaning of this bound is that if you find, if you minimize this ratio, so the minimization of this ratio is a good criterion to minimize the expected leave one out error. Okay? Okay. I think I am finished for the first. Is too soon?